Okay, it's my pleasure to try to explain a recent piece of research that we did. So I'm going to explain a bit of what we're trying to do and how you can all help. So I brought along, thanks for Teresa for making these. 他们没做发一张，把这个不是有2份吗？没做发。So we're going to hand out a prop for you to practice how to identify and classify galaxies, based on which we wrote a recent paper that was classified by hundreds of thousands of volunteers across the world. So just to start off with some basics. Galaxies, everybody has 2 galaxies in front of them. It's the same one, it's the same galaxy. And I think the way you got it, you have the same galaxy. Do I have one more? Is that okay? So you guys share. So if you take this apart, and I'm going to try to demonstrate this. Okay, you think they're the same. That's what you think. Okay. Okay, we'll do this. So we have a galaxy, and we're going to do an experiment right on the spot. I got the comment that these 2 galaxies are the same. Okay, put them down. Put the 2 galaxies on the table next to each other, okay. And you think they're the same. Okay, and I'm going to fix that for you. So you have 2 galaxies on the table and they look the same. Do they look the same to you? Yeah. Okay, then take one, turn it upside down and put it back down.
Spinning direction is different.
Let's see. Did everybody get that right?
Yeah.
Nope. You have to turn. No, this doesn't work. You have to actually take it out of the sheet and do this. Now they're different. Now there's nothing you can do to make them the same. Okay, did everybody get this right? So you have 2 galaxies, and they're the same, or at least this way they're the same. Now they're different. Now I've got 2 different galaxies. Okay. And just to make sure everybody has their 2 galaxies that are now different. Beautiful. And your galaxies are different. Good. So there is if you go to online to the Galaxy Zoo, and I believe Lauren informs me that our institute in fact made the Chinese version of the Galaxy Zoo interface, then you will see about 1 million such galaxies they'll give you one at a time. And one of the questions you have to answer for us is, what kind of galaxy is it? Let me see. This galaxy, the one you see on the screen, is called an S-type galaxy. It's S, like the letter S. Okay? And the other galaxy is called a Z-type galaxy. Everybody? Galaxy. Okay? And they're different. Every galaxy is one or the other, but not both. Okay? So in this database, there are about 1 million galaxies that we would like to identify. And so far, it's been people, volunteers, who go and click. Everybody can go and click, and you can help us do this classification of these 1 million galaxies. So far, there have been about 1.5% that have been successfully classified on this SZ question. And we need more. We would like to have 10 times, 100, many times more galaxies classified. And you can see it's not that difficult. Actually, since Lisa is a machine learning expert, maybe instead of having millions of people, we could have a computer do it for us. I'd love to know how that would work. Okay, so let me explain a bit about why do we care. How do people, why is this new? And why do we think this happens? Oops, other way. No. How do I go into?
Maybe we didn't switch.
So a few things just I'm going to explain about what this tells you about a galaxy. So a galaxy, most galaxies are what we call trailing spirals. So this galaxy is rotating counterclockwise. This one is rotating the same way. So here we go. And this galaxy is rotating clockwise. Okay? So these two galaxies rotate in opposite directions. And the question is, why do some rotate this way and why do some rotate the other way? And when I ask the question why, we could say, well, maybe it's random. There's no reason. It's almost the same as saying there is no reason. Again, my bar is, it's a good reason if you can predict which way it's going to rotate. Okay, if you can look at the neighboring galaxies and predict which way this one should go, that is a predictive description. Okay, so far I'm just going to try. Let me see. Restate this. 我们刚刚要讨论的是这些星系，有些是顺时钟转的，有些是逆时钟转。然后现在问为什么？这个为什么是我们能不能预言？就是你给我分类之前，可不可以预言这个星系该往哪个方向转？这个才算是理解。我看它的周围的星系，我可不可以预言哪个星系左转，哪个右转 ？Okay, just the basics that these galaxies, like our Milky Way, like one of these, consist of something like 100 billion stars, a lot of stars. But that's not the key point here. You can ask, why is anything rotating at all? Maybe that's the place to start. Why is our Milky Way, why is the Earth, why is anything rotating? And the context is that the current picture of the Big Bang is that the universe was homogeneous or smooth, and that's the same as saying that nothing was rotating initially. Okay, so nothing was rotating, and now things are clearly rotating. And why is that? In fact, there's a law of physics which would tell you this shouldn't happen, called conservation of angular momentum. If you're not rotating to start, you cannot end up rotating. That's just not allowed. So there's something fishy happening. There's something that needs some explanation. And this picture was first addressed by Simon White in 1984. And I'll try to explain a bit about what that does. 稍微再重复一下，是我们在讨论东西为什么会旋转。在大爆炸理论里面，宇宙一开始是均匀的，均匀的宇宙是没有旋转的，一切都是东西不在动嘛，就是均匀的爆炸。那一个不动的东西为什么会变成旋转？我们物理里面有一个角动量问题，角动量是守恒的，一个东西一开始不转，它不能自己转起来。所以这个转这个事情是一个需要解释的。那我先给大家看一个 play the movie. Yes, please. I'm going to show a simulation made by the TNG collaboration of how the formation of galaxies is simulated on a computer. So here, this is a real galaxy. Here's a computer simulation of how galaxies form out of a simulation from the Big Bang that has dark matter, stars, and gas. Of course, we only see the stars and the gas. And you can see that these galaxies form, they fly around, and they merge with each other. And sometimes you can see them having spiral arms, and you can see why. Why you can see that the spiral arms tend to be trailing arm patterns. And of course, just because you have differential rotation, the ones inside just wind up faster. So the trailing phenomenon is a generic outcome of a rotating object. And this is there's no sound. This is just a, it's just an animation of the simulation. So the good news is that we seem to be able to simulate objects that kind of look like galaxies. So there is, this is not violating any physics. The simulation also conserves angular momentum. That's good. And you form these things, and they do rotate. They do end up rotating. The reason, I'm just going to give you the big picture reason, is that you can see they orbit each other. It's like the moon orbits the Earth, and the angular momentum of the the moon's orbit around the Earth is much bigger than the rotational angular momentum of the Earth itself. So to rotate and conserve angular momentum, you can have the orbiting object completely dominate the back reaction. In the case of the moon, it's different. We happen to rotate in the same sense. But you could actually have a zero angular momentum system where the Earth rotated the other way. Well, actually the Earth couldn't really rotate fast enough to combine the moon's momentum even if you wanted to. But that's the basic picture. So this rotation, angular momentum, comes from the back reaction of neighbors. You can see galaxies interact, and the torquing by the neighbors causes the galaxy to rotate. I'm going to try to freeze this at a time when you can actually see the spirals.
Okay.
Let me see. Yeah, there we go. Yeah. Okay. So here you can kind of see the frame where the simulated galaxy looks like. There we go. It's the same sense. This is a what do you say? A Z-sensed galaxy in the simulation. Okay. So this is a actual. An actual galaxy Z, and these happen, and they are, well, this simulation was created to simulate a small number of galaxies, so it's a zoom-in simulation on a small volume, but there are many of these, there are billions of these galaxies in our universe that most galaxies rotate. So this is a very common feature, and there are two ways of saying it's understood. I mean, galaxies in simulation rotate. I'm not a fan of calling that understood. But if you can now ask, can we predict by looking at the neighboring galaxies, right? If you give you this picture, and can you tell me, should this be rotating this way or the other way? How would you know? Okay, how do you tell by looking at the neighbors which way it should go? And this is the subject of our recent study, where I'm going to see if I go back to the PowerPoint. Where we try to understand how this works. Thank you. Okay, let's see. Other way. Somehow it doesn't switch. Oh well. It says restart PowerPoint. Okay, no problem. This will continue. 刚刚就是要讨论我们第一，你看到我们我们电脑模拟里面也有跟我们看到的这个星系长得很像。然后也有旋转，然后你刚刚看到的是一个那个 Z 型的旋转方向，当然 这个方向当然是跟你看的跟你看的位置有关的。你在这边看是一个 Z 型，你在后面看是一个 S 型，所以每个人看的东西还不一样。所以你可以问问题 A 是不是 S 一个比一个多？这个应该不太可能。那我们yeah, no rush. Okay.
It doesn't want to go to the first slide.
Maybe we can try it on mine, if that helps. Here we go. Okay, so back to the picture. So this is the galaxy, a rotating galaxy, and we've seen how this works in both the simulation and in a real picture. Here is when you go to the website of the Galaxy Zoo, and here's a paper by Kate Land, where they go and give examples. So you can see most galaxies are much smaller and fainter, and it's actually not that easy, which is why most of those million galaxies look more like this. It's not quite as easy to tell which way they're rotating. And when you go to the website, you get these choices. You have to tell it is it a galaxy at all, and is it winding Z or S sense. And that's the information that we use to test this theory. Good. Now, just to go back and ask, why do things rotate? So if you look at the simplest case, if you just take a round object, if you think of a galaxy as collapsing from a round gas cloud, it cannot rotate. A round gas cloud has no choice, it will just get smaller. Even if you go to an elliptical gas cloud and you shrink it, that can still not rotate. So now life gets complicated because the simplest things that we know to calculate don't give you what you observe. So the lowest order where things can happen is you need a twisted ellipse. Okay, so you have to not only make it not round, you have to make the ellipticity axis change radially. And if you take a twisted ellipse and shrink that, that will rotate. Okay, so that's the minimum you need. So when you predict the spin, and you can see these two result in, I'm going to get this wrong. This is an S, and that's a Z oriented galaxy. That this depends on whether your neighbors, as you go out, shift left or right. Okay, so what we do, I'm jumping over a lot of details, but to get to the end, in the Galaxy Zoo, as I said, we have 15,155 galaxies that have been successfully classified, a tiny number, 1.5%, because those are the big ones that are easier to do. And from them, we can look at the predicted orientation by looking at the neighboring galaxies. And you can see that there's an angle between the rotation you expect and the rotation that's measured, and it correlates such that the ones that should be rotating do align more so than a random sample. So here we have the first measurement, the first prediction, and experimental confirmation of the origin of angular momentum. 所以我说明一下，我们这里就做了这个事情，就是拿了这个100多万星系里面，大家群众，像我们这样的，自己投票分类的星系，成功分类的有15000个，就是只有1.5%是成功分类的，所以大家可以帮忙，我可以请丽莎老师帮我们用机器学习来，搞不好可以5分钟搞不好可以分类我们所有的星系。现在这个成功率还有点低，然后我们之前拿1.5%就已经看到这个角动量跟它周围星系预言的角动量的比值，这个趋势已经存在了，所以现在只需要分类更多星系，我们就可以做精准的宇宙学。 Uh, um, this is my story for the evening of our recent results of doing something relying on the broad public. Okay, this is science that was made possible by citizen science, voting on the Galaxy Zoo website using the SNZ information that everybody gets, and that has never been used scientifically. There's never been an attempt to understand why do some wind left and why do others wind right. And the hard work of all these volunteers is now paying off. We actually now understand something which we didn't understand and couldn't have understood without the input of volunteers. So 这个谢谢全世界各地的群众，非天文学家就是爱好者，在用眼睛看这些图像投票，回答了我们这个角动量来源的问题。Great. Thank you. And if anyone has questions, I'm happy to talk and now or later.
Is there any effect from the cosmological vorticity field? I know that in linear scale there is no, because vortical flow doesn't grow up in the linear scale, but in non-linear scale there is such a vertical flow in the effect on the spiral galaxy.
Thank you. That's a very technical question about the vorticity of a flow in the universe, and I'm happy to talk to you sometime over. I think we will need more beer to do it justice. Just a few comments. Vorticity is another very special property of fluids that is conserved at all orders of perturbation theory. So even more so than angular momentum, it's something called Kelvin's circulation theorem, that if you have no vorticity to start with, and our universe had no vorticity to start with, then you cannot generate any at any order in perturbation theory, up to infinity. Now, of course, these galaxies have plenty of vorticity, so there are reasons why this fails, and that comes from shocks and other phenomena. And these shocks are induced by tidal talking. As I said, it's very long and technical. I'm happy to talk to you, but it is complicated. Yes?
Yeah, how does time affect the dancing galaxy?
Let's see if I can get to the movie again. So the question is, over time, what happens? And calling them dancing galaxies is not an exaggeration. They're going all over the place. They're not staying put in one place. In fact, even the identity of galaxies changes because objects merge. So you have multiple galaxies merging together that turn into a single galaxy, and over time, merger means you cannot even really talk about a single object. And if you watch the movie, you may even see that the alignment changes with time. So sometimes that main galaxy will be S-like, and after a merger, it could become Z-like. Okay.
If there's no significant force outside the galaxy, and if there's no merger, then will the shape stay the same?
Yes, because angular momentum is conserved. So you need something to actually hit it to change the way it rotates. And again, that's.
What about a star dying or a star being born within the galaxy, like a major star? Would that affect it?
Okay, so within a galaxy, your conservation of angular momentum is exact. With other words, if I'm standing here and I'm not rotating, there's nothing I can do to myself to make myself rotate. So a star, conserving momentum, it cannot be done. Doesn't help. It has to be an external force. Okay, so that's why it's such a clean predictor, because there's nothing a galaxy can do to itself. It's like when I was a kid in Germany, they have a story. I don't know if anybody else ever hears these stories, called Baron Münchhausen. It's about a fellow who likes to tell lies, And one of his lies is how he sunk into a marsh and pulled himself out by his hair. I don't know if anybody heard that story.
Does his nose get bigger?
That's Pinocchio.
Okay, I didn't know if that's what I'm thinking. Maybe that's
There was this fellow who claims he pulled himself out of a swamp by pulling on his own hair. And as you can see, there's some conceptual problem in physics that you can't really do that, because the more you pull, you cannot make that a net lift. And similarly with rotation, there's nothing you can do to make yourself either go up or rotate. Both are not possible.
a good analogy.
Yes.
Is there any preference for S or to Z galaxy?
Very nice. We just had another paper on that very recently, of whether there is a preference over S to Z. And the short answer is, in those 15,000, there is a preference. It's 49 to 51 voted by people. And people have done experiments on that. So what you do is you take an image and you randomly flip it before you ask. And of course, an S will turn into a Z when you flip it. But then you can ask, well, if you just randomly give people galaxies with exactly 50-50 chance, people will still vote S more often than Z. Okay, so the human eye is not symmetric. People like seeing an S more than they like seeing a Z. There's a eye bias. So there is such a bias, and there's nothing to do with the galaxies actually being more S or Z. It's just with the human eye. Somehow people, maybe because we're all left, they're more, right-handed people that vote that way. And the universe as a whole, so that's something if you try to correct for it, there's no evidence. And of course, we don't expect, there should be the same number of S and Z galaxies. That's what I would have guessed. But a deeper question is, there is something called helicity, and that's similar to vorticity, is that some forces of nature are chiral. So the universe is left and right, for the weak force, maximally asymmetric. So neutrinos are only left-handed. So there are things in the universe that are, for example, sugar is left, I think, handed. It's a left-handed molecule, and there's no natural right-handed sugar in our planet. You can make it in the lab, but not naturally.
Does it taste different?
That's
the important question.
Okay, what I heard, and again, you should look it up, so don't take my word, but I'm not a chemist. But they taste the same, equally sweet, but you cannot actually burn it. So you can have sugar that tastes sweet but does not make you fat.
That's good.
There we go. So.
It doesn't cause cancer.
That I'm afraid I know even less about. That's a much harder question than the rotation sense of galaxies. But to just finish off Paula's question of is there a symmetry? And there's a question that is possible is if you take two galaxies near each other, you can ask, is the galaxy in front more likely to rotate left compared to the one behind it? Okay, and that is allowed, and as I said, for some forces of nature, that is maximally violated. And we looked into this projection onto helicity of all these galaxies, and there are a couple of possible outcomes. You could have them equally left and right helical. You can have them preferentially left or preferentially right. 3 possible outcomes. And the data allows 2 of them, but not the third. So symmetric is allowed, left is allowed, right is not. So there's already constraints on this question from just this very small data set. And I think the exciting thing is we just need either more volunteers or a machine to classify the remaining galaxies.
Oh, I got it back.
Beautiful. So you can watch this movie a little bit and you can see, the question of, does it change? And as you can see, these galaxies, these rotate in opposite directions, one S, one Z, and then they're going to merge. And you can see that after the merger, it cannot follow the sense of both. That's not possible. It's got to pick one. Okay, so there's lots of complexities, but in the end, it is still a predictive process. This is the credit of this is that's the TNG simulations by Vogelberger's group at MIT that made these beautiful movies.
So here they only show the visible light in visualization.
I believe so. This is, I believe, the stellar and gas that.
Now, when these
Not-
galaxies merge, I imagine it's like a pretty chaotic process. I mean, for like if a galaxy merged with the Milky Way, that probably would not go well for Earth.
Oh, it will. So in about, I don't remember, a few billion years, the Andromeda Galaxy is going to merge with the Milky Way. That's going to happen. Just have to live long, and then you'll watch the merger. And I think it may actually merge before our sun burns out. So you really only have to you don't even have to leave the Earth to watch that. It is spectacular that you have now two Milky Ways in the sky. Because right now at night there's one Milky Way, and then you'll have a second one coming down. But it turns out it doesn't do anything to anyone on Earth. So the nearest star that comes by is still a long ways away. It doesn't actually change anything on Earth measurably that just pass through each other, because it's mostly galaxies are almost all empty space. So the space between stars is so large that out of the 100 billion stars, none of them are going to collide. So, less than 1 in 100 billion will actually collide on this merger. So these stars, when they merge, do so what we call collisionless. So sadly, it's very peaceful. No violence in this merger. No, with a Death Star. Somebody likes violence here. No Death Stars involved.
Any other questions? If not, then thank you very much.
Thank you.
Okay, then I'll see if I can get my laptop to work to go to the last round.